Good morning, students. We started our last chapter, that is gas absorption and stripping. Last day, we have seen how to calculate the minimum liquid flow rate for absorption and minimum gas flow rate for the stripping. Actually, minimum flow rate calculation of minimum flow rate is required for a particular system, and then operating gas or liquid flow rate, generally it will be in the 1.2 to 2 times of this minimum flow rate. That is the, and this what is the times, that is based on our industrial experience. But what will be the minimum, and then that factor it is, that will be operating. So minimum gas flow rate or liquid flow rate, it is required, okay, because this is in our hand, and our always objective is I want desired separation with minimum liquid flow rate for absorption, and for steeping I need my desired separation with minimum gas flow rate. But if you get a minimum, means it will reach it, minimum means it will reach to the pinch point. Pinch point means where driving force is 0, and closer this, then the height of the column will be very high. So but this is one concept I have to first calculate, then you will keep the liquid flow rate 1.2 to 2 times of minimum flow rate, then I will recalculate the whole thing. So this is the concept, okay. So today we'll more discuss about the design of pack tower. So generally we will do the two things. One will pack tower first, then we'll discuss about the plate column for absorption and stripping. The constructional feature of packed column have already been described in previous chapter. So in previous chapter 5 we have discussed in detail that the constructional feature of the packed tower. The packed tower and the plate tower are the two column choices for carrying out the gas absorption operation. In a plate column, the gas and liquid phases are come in contact in discrete stages. So you understand, different plates are there. So they are liquid and gas are coming in contact in plates. That means that the discrete stages are there. So it is called stage-wise contact. The gas and liquid concentration undergo step changes from one plate to next. In a packed tower, on the other hand, the liquid flowing down through the packing material remains in contact with the upflowing gas at every point of the packing section. But in packed air, it is liquid is flowing continuously from the top and gas is flowing continuously from the bottom, and there is a continuous contact between liquid and gas. Also, the concentration of the both phases changes continuously. So, packed tower is called a continuous differential contact equipment. So, you can means homogeneity. Okay. So, sizing of a packed column basically includes the following steps. First, I have to select the solvent, that already we discussed how to select the solvent. Selection of packing, it is discussed in chapter 5. Okay, what type of packing I should use, and it depend, and always my objective will be if I can make more surface area. Okay. Determination of minimum actual solvent flow rate. First I will determine the minimum, then actual flow will be 1.2 to 2 times of minimum, that already we discussed. Determination of column diameter. So that also already we discussed in chapter 5, how to determine the column diameter based on the flooding condition. Okay. So these four things we have discussed. So today what we'll do, determination of the packed height. So yeah, if I know the column, okay, everything we know, just if I diameter is known, now if you can calculate this height of the column, that's mean I have done this job. After that, design of liquid distributor, reduced distributor, packing support nozzle, etc. These are the mechanical part of this thing. Okay, so these things are possible. So now our objective is to determine the height of the packed tower, and the packed tower is a continuous. Okay, the first four steps have already been discussed. In this section, we shall concentrate upon the height of the packing required for a particular separation. The discussion will be confined to the case of transfer of a single solute. I told it is, I will take the single solute. The following items and variables should be known or available before the design purpose. So once we don't design, I need this thing, that equilibrium data is required for a particular system. Always I told, if you see, always I draw the equilibrium curve that is required. Flow rates and terminal concentration of gas and liquid phase, and I told that flow rates will be given. Okay, just like I told that for absorption, gas flow rate will be known to you as per problem statement, that inlet concentration, exit concentration will be known to you. Okay, then which solvent, once you select the solvent, then concentration, initial concentration will be known to you. Then you calculate the minimum solvent flow rate, then actual flow rate 1.222 times of the minimum, so that things, and from the material balance you will get the all the flow rates and terminal conditions. And also with this thing, individual and overall volumetric mass transfer coefficients, sometimes called the capacity coefficient, KYA, small kya, kxa, capital Kga, Kl, etc. So these are the mass transfer coefficient which we discuss in detail in chapter 3 and 4. Always this required, this mass transfer coefficients are required, that always already we have already learned this. So now we are a position to design the column time, means we are in a position to determine the height of the column, because we know that how to calculate the diameter of the column. Now I will determine the height of the column. Now if you take one column, okay, so gas is entering here, H equal to 0, and it is going up, okay, 1 2, and liquid from top it is pouring, and this is a continuous. So if it is a continuous system, I can make the differential version. So this is the basic concept. If you see everywhere where the system is continuous, so then you take a small volume del H del V volume and make the balance, either material balance or energy balance on this section, then you integrate. This is the concept. If you see in each, in respective of any course, heat transfer, whatever you have course you have seen, if you see when the system is continuous, then this is the generic approach. Okay, so take a small volume and then make balance on this, then you integrate, because if the continuous, for integration can be done in continuous system. This is mathematics, it is still. So for this system, I consider the pack tower as shown in this figure. We use mole fraction unit. Here I have used the mole fraction unit. You need gas and liquid phase concentration. Okay. Now, what is G dash? G1 is the gas flow rate, but G dash is the gas flow rate per unit area. So I am making the calculations per unit area basis, because you know what will be the column diameter, that will be determined in other. So that is not my, whatever diameter it is not required for me. I have to determine the height. So I have taken this, that column area. This is the unit area. Okay. and that specific interfacial area for this packing material meter square per meter cube. So this is depending on this particular which packing material you are taking, that will, it depends on that. And liquid flow rate also per unit area. So that means the cross section of this column is unit area. Okay, now taking the mass balance over a small section of column DH. So if I go some after age, after height it, if I take this DH, so what is the entry of gas? G dash into Y and L dash into X. So this is the concentration of gas. Okay, G dash is the gas flow rate per unit area, Y is the corresponding concentration in mole fraction, L dash is the liquid flow rate per unit area, X is the that mole fraction concentration. So this is the thing, it is, let's check it is this. Now let's take this is absorption is going on, so that mass transfer is happening from gas phase to liquid phase. That rate of solute, okay, will change. Okay, flow rate of solute will change. How much change? For DH, that is, so here rate of solute flow rate will be G dash into Y. Okay, moles per time area, rate of, isn't it? So this will be my solute flow rate. Now change in solute flow rate over the section del H, that is dg dash, g dash Y, and this is negative value because in case of gas absorption, mass transfer happening from gas phase to liquid phase. Okay, let's take Na be the local flux and Ky, small k, is the individual gas phase mass transfer coefficient, and the then volume of the packed bed or differential section del H, because del H is height and section cross section of unit, so volume is 1 into dH. So interfacial contact in the differential section of unit cross section area will be, this is the volume and this is meter square per meter cube, so this will be the interfacial. So rate of mass transfer, the solute, it is, this is the ADH is the mass transfer area and this is the flux. Okay, so then that will total mass transfer in DH area, DH height will be, this is the mass transfer. Okay, now this I am getting from the mass transfer concept. Now I will give the mass balance, the elemental one. So what is the this? Whatever the mass transfer will happen, means whatever mass transfer will happen from gas phase to liquid phase. Okay, this is the term, and this will be equal to how much loss of solute in the gas phase. So this is the G dash is the solute flow rate, differential of this with negative sign because it is decreasing. So minus, if I make the differential, minus G dash dy minus y g dg dash. Now if you see G dash, what is this? This is the total flow, carrier gas plus solute. Okay, since carrier gas is not solute, the change in total gas flow rate is also equal to the rate of mass transfer in the solute. So whatever dg is changing, means how much total mass transfer is changing, that mass is transferring to the other, means that will be equal to this. Okay, so this is, so that's mean d minus dg dash, how much mass is decreasing from the gas phase, that it is getting transferred a dh into na. Okay, so if I put this d dash equal to a this one, now if I take this one into here in this here, then it will be a dh na 1 minus y equal to minus g dash dy. Now na equal to, I know what, 1 equal ky into y minus yi. Okay, that is the thing I know. Okay, so this is the thing, I am not taking overall mass transfer, I am taking the gas phase. So na equal to ky into y minus yi. So dh, if I put this thing here, okay, now dh will be minus g dash dy into ky into a bar into 1 minus y into y minus y. So this is my differential balance from the material balance. This is the differential equation I got for the packed tower. Now what I have to integrate this one? Integrate height 0 to h. Okay. Now what will be y1? y1 to y2. So this is the concept. Okay. 0 to, so integrating this one means I'm taking from bottom to height in at point 1 y1 I want to 2. Okay. So this is the thing I have to integrate this one. Okay, so height ht equal to this height of the column. So I have to integrate this part. Okay, now if you see here integrating this part, it's not so easy because let's say you have this particular y1 to y2. Okay, so now you want to go from here. Now once you want change the y, okay, so numerically, so from you start from this and del y you go in this way and then you go this, but when you are changing the y, then your yi is also changing, because let's take if you this is the y value for a particular thing, so then you could take minus kxy, this will be yi and this will be xi. So for every, so yi is not a constant. Okay. so so in yi is a variable of it changing with y. So that's mean you have to integrate it numerically. Okay. So that you that's why evaluation of above integral gives the height of the packing. Okay. So this is the integration. The integration is not straightforward. Seen interfacial concentration yi is not explicitly known as a function of the variable of, because it will keep changing, and every time you have to whatever the yi value you have to take this slope and you will get this one. Then you have to determine this one. Okay, so that can be done through as mentioned below. First, what will you do? First, I will draw the equilibrium curve xy. Okay, for a xy plane for a particular gas system. Then I draw the operating line with material balance. Okay, so gs into capital Y1 minus capital Y2. So y1 minus y2, okay, capital. So accordingly I express this in some mole fraction. So this way I will draw this curve, that we know this one. Okay, once I will do this one, then what I will do, for each y point I will take, so y1 and y2 know. Now each y point I will calculate the yi through this one. Once I will get this yi, then for a particular y, I will calculate that this integral part. Okay. So what is the function? The f1. So if you take this one, this is g dash divided by ky a bar into 1 minus y into y minus yi. So that's mean if you take this function fy, so fy equal to this into dy. Okay. So for a particular y, I will calculate the fy with this equation, because, and then I have to make, once I will get this y1 to y2, okay, that this thing, now I will integrate this numerically area under the curve, and either trapezoidal rule or Simpson one you have studied in numerical analysis course. So this way you have to, an area under the curve will be height of the column. Okay. So here today we have seen how to calculate the height of the column. And for packed tower, keep it in mind, packed tower means it is the continuous process. So if you have to make the differential balance and then The height you will get through the numerical analysis, because here you cannot integrate it in analytical. It is not possible. So once you will get this thing, that will be height of the column. So let us stop today. To next day we will see the other part. Thank you.